We will learn about the Gauss's law, but before that we have to go through this topic, which is continuous charge distribution. So far, whenever we talked about a charged body, so let it be a charged body, we always consider that charge is concentrated at a point, at the middle point of this object, of this charged body. And this we call the point charge, and for this matter we also extended it to electric force and electric field. But in reality, charge is not concentrated at the center, but it is spread throughout the space. So charge is spread equally throughout the space of that object, and that we can say that this is charge distribution. So there are three possibilities about charge distribution. So in the first figure, what you can see, there is a line. So this line is there, okay. Line can be a wire, okay. So it has only one dimension, only the length. Now if we say that the wire or the line is charged by charge Q, then this Q charge is distributed uniformly throughout the wire, throughout the line. So Q is distributed, broken up, and it is continuous. It is equally everywhere throughout this wire. And let the total length of this line is L. And if we break a small distance from this line, if we take only a small distance, and that distance is called delta L, what you can see here. Now then what would be the amount of charge in this small length of the line or the wire? And let's say that small amount of charge is delta Q. It's not whole charge, but small amount of charge, and that is actually delta L multiplied by lambda. And what is lambda here? Lambda is actually the real charge distribution, and lambda is actually total charge by total length. That ratio is lambda. So charge distributed over the length L, and this ratio is lambda. And using this, we can think about the charge distributed upon this small length delta L, and that delta Q, the small charge in that length delta L, will be lambda multiplied by delta L, and we call it line charge distribution or line charge delta Q. Now let's talk about the surface charge. Now for that we have to consider a surface. A surface is a two-dimensional space. It has area, okay. So in that area, the total area of this surface maybe is the S. And here if we take a small amount of this surface and we call it delta S, a small amount of the area. So we want to find out what would be the charge in this small amount of area. For that, we should understand that there is something called surface charge density, and that is sigma. Sigma is called the surface charge density. And what is sigma here? Sigma is actually total charge, okay, by total area. All right. So now if we want to find the charge at the small area delta S, then this small charge delta Q would be small area multiplied by this sigma, and we call it surface charge delta Q, okay. Or and sigma is surface charge density. And finally we have volume charge. So just think about a volume, okay. think about maybe a sphere and a condensed sphere which is not hollow, then the charge Q, the amount of charge on that sphere Q, is actually distributed throughout. And that distribution is of this kind. So rho is the charge distribution throughout the volume. And this is actually total charge divided by the volume. Okay, and in that volume, if we take a small amount of volume, that is called delta V. So if you want to find what is the charge in that small amount of volume, for the small amount of volume, what is the charge here? So this charge is delta Q again, small amount of charge, which is actually in that volume multiplied by the volume charge density. And for that matter, we have different units assigned to the new topic, the charge densities. So for line charge density, that is lambda. So the unit of lambda is coulomb per meter. That of the surface charge density, sigma, is coulomb per meter square. And that for the volume is, that is rho, is coulomb per meter cube. So I talked about the charge density, and sigma is equal to total charge by total area. For example, here I have shown it. And in the book, you can see that actually sigma is written the small amount of charge by a small amount of area. So both are the same thing. You don't have to worry about these. Because charge is distributed uniformly, continuously, so it means equal amount of charge is at a unit area, given unit area. So in that way, both the ratios are giving the same value. Alright. And finally, if we want to find the electric field due to this small amount of charge, delta Q, or for the charge distributed over a small region or small length, delta L, then how can we find the electric field? For that, we simply see that where do we have to find the electric field? And we have to find electric field at P due to this small charge delta Q. And what electric field formula says that E is equal to 1 upon 4 pi epsilon naught charge, which is delta Q, divided by the distance between the charge and the point. So this distance we are talking about, okay, which is given r dash. Okay, now before that, because origin is here, and from origin the charge element is r distance away, and the point where we have to find the electric field is capital R distance away. So for that matter, our actually what we are finding here, the radius or the distance is actually capital R minus small r square, okay, which is written as r dash, okay, so it will be r dash square. So we can write it again, 1 upon 4 pi epsilon naught delta Q by r dash square, and since electric field is a vector quantity, it will have a direction element which is r dash cap, okay. But we know that delta Q is actually delta L multiplied by lambda. So instead of delta Q, we will be writing lambda delta L. So our electric field will be 1 upon 4 pi epsilon naught lambda delta L divided by r dash square, a scalar here, only the magnitude, and then attach a direction element. Alright, so this was for the line charge delta Q, that is lambda delta L, and you will get the same result for all the other options. Like if it is surface charge, then just replace lambda delta L by sigma delta S, and for the volume charge you will replace it by rho delta V, and rest of the things will be same because the value of r dash, everything is the same. Now let us understand what is the problem part here. We can use this so beautifully, so easy. I've done the calculations, but just think about if we change the point, the test point charge from the given point to some other point here. In that case, the value of r will change, the value of r dash will change. Okay, so in that case it will be very difficult to, if we have to find the electric field due to a big chunk of charge distribution. So in that big chunk of charge distribution, there are many points where the value of r will change, r dash will change. Okay, so in that case it will be very difficult mathematically to find the solution of the electric field. What I'm trying to say that rho r dash and the vector element of r dash, the direction element, will change, all will vary point to point for mathematical calculations. So that's why Gauss came up with a wonderful idea to deal with this situation and find the electric field in a very simple way, considering that the charge, though distributed uniformly over a volume or over an area or over a length, can be considered within a space, and that space is called the Gaussian space, and he used the concept of electric flux. Okay, so if you have gone through the flux that I've dealt in previous videos, so the flux is actually the vector E multiplied by the area element, and this multiplication is a scalar multiplication or the dot product. So E dot delta S is the flux or the flow of electric field or electric field lines, and E dot S is actually, mathematically, it is E delta S cos theta, where theta is the angle between electric field and the area element. Let's focus on the figure here, figure 1.22, in which a charge is there and a sphere is drawn. This sphere represents the Gaussian space, the Gaussian sphere, the radius of which is given r. Okay, and it has area, okay, in which we have just taken a small area delta S, and this area is a vector quantity because this area, maybe if we draw it here, has a different direction. Okay, and the direction is the radial outward direction. Okay, and due to the charge, the electric field has also the same direction because it is a positive charge. So the electric field line will be radially outward. So the electric field has a direction, the same direction as that of the delta S. And suppose if we talk about the direction of electric field right here, where we have done the second area element, here also this is the direction of area element, and the electric field will have the same direction, okay, that of the area element. And since the angle between the area element and the electric field is 0, everywhere it is 0, then our cos theta will become cos 0 degree is equal to 1. So we'll only focus on E multiplied by delta S. And as we know, E is actually equal to Q upon 4 pi epsilon naught R square. This R square, okay? And then we have to multiply it with delta S. Okay? So Q upon 4 pi epsilon naught R square and multiplied by delta S. So for a sphere, for this sphere, the area of the sphere is the total area. So if we want to find the total flux is actually just phi, and total flux will be Q upon 4 pi epsilon naught R square multiplied by the total area, and total area of a sphere is 4 pi R square. And if you cancel out all the values like 4 pi and R square, then what is left is Q upon epsilon naught. So electric flux through a closed surface, okay, which encloses the charge inside, is always Q upon epsilon naught, and that is called the Gauss's law. So what Gauss's law says, that electric flux through a closed surface S is equal to Q upon epsilon naught, and Q is the total charge enclosed by S. Now let us apply Gauss's law to find the electric field due to a wire where the charge is continuously distributed. So a continuously charged wire. And this wire is too long, you know. So suppose, for example, if I say that I have to find charge due to this at a point here, for example, then it will give this direction. At this point it will give another direction, another direction, another direction. So electric field due to given points on this charged wire will give several electric fields in different directions, and then we have to do the vector sum, so it becomes so tedious. That's why Gauss's law makes it so easy, and we are going to apply it now. To use the concept of Gauss's law, first of all we have to make a Gaussian surface, okay, an enclosed Gaussian surface. So let's say the length of the wire is given L, and we make this length of the wire, we put it inside a cylinder. A cylinder is a closed surface. Now we know that phi, electric flux, is actually E dot delta S at point P. So at point P, the area vector is multiplied by electric field, and that is the flux. But when we apply Gauss's law, so this E dot delta S would be actually E dot S cos theta. Okay. For the curved surface area of this cylinder, like here, the area element has a direction, and the electric field due to the continuous charge distribution is also in the same direction. So actually E dot delta S is E dot S, because this cos theta becomes 1, because theta is here 0 degree. There's zero angle between E and delta S. Alright, but if we want, because for a Gaussian surface we have to find all the possible areas where we can find the flow of electric field. So suppose at the bottom the direction of the surface will be this, and at the top the direction of the surface will be this. But electric field is always radially outward. So if the charge is here, it will be radially outward. So at this point, the angle between the electric field and that of the Gaussian surface delta S is 90 degree. And when cos 90 has to be multiplied, so cos 90 is actually 0. So that's why the electric flux through the top and through the bottom, because here also the same condition will apply, the direction of the electric field and the area element is 90 degree. So top and bottom we have to cancel, because this will not give any value to the electric flux. Alright. So you literally don't have to write all these things in exam. I'm just giving you the idea how it works, how we only need to stick with the curved surface of the cylinder, of the Gaussian surface we imagined. So for the Gaussian surface what we have made, which is a cylinder, we are ignoring the top and the bottom part, and we only focus on the curved area. And through that curved area the flux is E. Okay, we ignore the vector here, we focus only on the magnitudes. So E and delta S. So this is the flux. Now total flux would be E multiplied by the area, and the curved area is actually 2 pi RL. Okay, we are ignoring the top and the bottom. We are only focusing on the curved area of the cylinder. And we are here to find the electric field at the point P, which is R distance away from the line charge, what we can see here. So this is the flux. This is the total flux. And according to Gauss's law, the flux is actually equal to charge, okay, which is Q upon epsilon naught. This is what the Gauss's law says. So flux is actually equal to Q upon epsilon naught. Now these are the results of flux. At one point it says it is E multiplied by 2 pi RL, and at the other end it says flux is equal to Q upon epsilon naught. So we can equate these equations. So we can write E 2 pi RL is equal to Q upon epsilon naught. But here E 2 pi RL is equal to Q is, for the linear charge distribution, it is actually lambda L and upon epsilon naught. And now you can cancel out. You can cancel out L, which is both sides. Okay. And what is left here is E is equal to lambda upon 2 pi epsilon naught R. And that's it. This is the electric field through due to a long wire of charge distribution lambda. Now since electric field is a vector quantity, so we have to add one vector element or the direction element, which is simply, we will write an n sign, n cap, which is direction is always in radial outward direction, and that can be given by n cap, and E is a vector. So this is your derivation of electric field due to a long wire of charge distribution lambda using the Gauss's law, which is in few simple steps. That's it, only this much. And the same can be done for volume charge distribution and for area charge distribution. What you can see, this is for the area charge distribution, and this is for the volume charge distribution. Okay, so it makes it so easy using the Gauss's law to do the electric field. Okay, it is a bit more about understanding the imagination, how the Gaussian surface is imagined. So I'm gonna leave you here. We are done with all these topics, and I request you guys to go through each and every exercise at the end of the chapter. And if you get stuck somewhere, I just give you one website where you can actually check the solved questions. That is www.proteacher.in, okay, /physics. If you it's /12th and then /physics if you want to stick with the 12th physics. And just go to the website www.proteacher.in, where you will find all the solutions of NCERT questions also, and notes and many helpful materials out there. Okay, thank you for watching. Now next time we will meet when we deal chapter 2.